Solve x squared plus 2xy squared plus y is equal to negative 27, and x plus y is equal to 3 for x and y. So this is a system of two equations in two unknowns, and the two different unknowns are x and y. Furthermore, the first of these two equations here is a nonlinear equation, and the second one is a linear equation. So we have some work to do here. There are a lot of different ways to proceed, but one way to proceed is to take the easier looking of the two equations, which is the second one, x plus y is equal to 3, and solve this equation for x. The way you solve this equation for x is you subtract y from both sides of the equation. When you subtract y from the left-hand side of the equation, you get x. When you subtract y from the right-hand side of the equation, you get 3 minus y. So now we have x written in terms of y, and we can take that expression right there for x and plug it into this first equation everywhere we see an x. When we do that, what we will have is we will have an equation in y alone, and now we're down to just one variable at a time. So I'm going to rewrite this first equation here over here, and that first equation is x squared plus 2xy squared plus y is equal to negative 27. Now, everywhere that I see an x in that equation, I'm going to replace it with 3 minus y. So this becomes 3 minus y squared plus 2 times 3 minus y times y squared plus y is equal to negative 27. So on the next step, I'm going to square out this expression right here, and I'm also going to multiply through here, and we're trying to turn this into a third-order polynomial. So when I square out that first term, what I get is 9 minus 6y plus y squared. Now you should do the FOIL exercise on this expression to make sure that this is what you get. Now this term right here, we have 2 times 3 times y squared, so that is going to be plus 6y squared. And then for the next term, we have 2 times minus y times y squared, and that is going to be negative 2y cubed plus y is equal to negative 27. The last thing to do here is to collect terms, and we have a number of them. First of all, we have one cubic term, we have 2 quadratic terms, we have 2 linear terms, and 2 constant terms. And we'll start with the highest order first. The highest order cubic term we have here is negative 2y cubed, so that comes first. In terms of the y squared terms, we have a positive y squared plus 6y squared. That will give us a total of 7y squared. Then we have a negative 6y plus 1y, and that'll be negative 5y. And then we have plus 9 is equal to negative 27. Now the next step is going to be adding 27 to both sides, and when you do so, you just get this same expression. When you add 27 to the left-hand side, you get 36, and when you add 27 to the right-hand side, you get 0. Now, most people at this point would, because there's a leading coefficient out here, which is negative, they would multiply this through by negative 1. That doesn't change the solution, but most people would multiply it through by negative 1 and they would get this as the polynomial they want to solve. Now, there is something that is known as the rational zeros theorem. I'll write that off to the side here. And the rational zeros theorem is used to give you some candidates for what y values might solve this. Trial and error is too difficult here. Well, what the rational zeros theorem says is if you take the factors, and the factors both positive and negative, of this constant term here, 36, so those factors, of course, are going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 9, plus or minus 12, plus or minus 18, and plus or minus 36. And then you take the factors, both positive and negative, of the leading coefficient, which in this case is 2, and that's going to be a little bit easier. You get plus or minus 1 and plus or minus 2. And if you take the ratio, that is why they call it the rational zeros, of all of these numbers divided by these numbers, you get all of the possibilities for what might be zeros. So when you take the ratio of all of these numbers divided by all of these numbers, you get a very long list here. And that list looks like this. Plus or minus 1, then plus or minus 3 halves, and that's taking this 3 here and dividing by 2, plus or minus 2, and the list goes on until you get the last ratio here, and that last ratio will be plus or minus 36 divided by plus or minus 1, so that gives you plus or minus 36. Now, those are all the possibilities, and I could try synthetic division with all of those possibilities, but I'm going to pick off one of these that I'm going to look at specifically, and that is y is equal to 4. Now, y is equal to 4 is one that is going to work. It is actually going to be a root of this polynomial right here. So let's do synthetic division to find out what the remainder is. So here's the way you do synthetic division. You put the 4 right here, and then you put the coefficients 2, -7, 5, and -36 up above here. So this is 2, -7, 5, and -36. And as we did 2 videos ago, this 2 simply drops down, and then at that point it is just multiply and add. 2 times 4 is 8. 8 plus a -7 is a positive 1. And then you multiply. 1 times 4 is 4. 5 plus 4 is 9. 9 times 4 is 36. And -36 plus 36 is a remainder of 0. If you would have tried that with any other number in this list, you would have not gotten a 0 remainder. So what this tells us, this piece of synthetic division right here, is that our polynomial, which is right here, and let me go ahead and write it out, 2y cubed minus 7y squared plus 5y minus 36 equals 0, it can be factored. And one of those factors is going to be y minus 4. And y minus 4 will get multiplied by a polynomial that is 2y squared plus y plus 9. And that's equal to 0. So we now know that there is one root, y equals 4, but we have a quadratic here, and that quadratic might have two other real roots. So I could use the quadratic equation, but when I use the quadratic equation, here's what I get for a discriminant. And the discriminant is the part underneath the square root in the quadratic equation. That is b squared minus 4ac. And I am working with this polynomial right here, this quadratic, which has 2, 1, and 9 as a, b, and c. So when I compute this discriminant, what I get is I get 1 squared minus 4 times a, which is 2, times c, which is 9. 4 times 2 is 8. 8 times 9 is 72. So we get 1 squared minus 72, which is negative 71. So the upshot of this is this cubic polynomial has one real root, and that one real root is y equals 4. And because the discriminant is negative, it has two complex roots. So really the only root we need to worry about in solving this equation is y is equal to 4. Now once we have y equals 4, we come back to the original set of equations and we want to determine what x is. Well, obviously the easier equation to plug into is going to be this one. When y is equal to 4, you can see that x is equal to negative 1. So x equals negative 1 and y equals 4 is the one point where these two equations are both satisfied. There are no other points. So you can write it in this form right here, or you can also write it as an ordered pair. xy is equal to, forgot the negative over here, negative 1, 4, and that is the solution to this 2 by 2 set of equations.